Welcome to the 12th lecture on risk management and insurance. In this lecture, we discuss the concept of certainty equivalent. The material in this lecture and the next one will be quite demanding. The mathematics is not difficult, but just the concepts are quite demanding to understand. So I would like to review first what we have done in the last lecture in this graph here. Remember, we deal with a fair game. With 50% chance you win $8, with 50% chance you lose $8. The game is fair, so the expected value of the game is actually just the initial wealth that you have. Now, this can be applied to insurance. So, for example, with 50% chance you're healthy, and with 50% chance you're sick, so then your wealth will be lower. But in this lecture, I will actually stick to the terminology of a game, and will not yet mention insurance so much. So with 50% chance, our wealth is here, and our utility will be so much. And with 50% chance, our wealth will be low, our utility will be low. And so the expected utility, because it's 50-50, is just in the middle. And also here, point B is just in the middle along this dashed line here. So that's the expected utility of the risky prospect. Now, if we do not take part in the game, then our wealth will be constant. Okay, we just have initial wealth and that's it. We don't play. In that case, our utility will be up here, and that's also our expected utility, because the expected utility of a constant is just a constant itself. So a person with a concave utility function is risk averse. That person will not take part in a game, even when the game is fair, 50-50. The expected utility of the game is less than the expected utility of not playing the game. So the concavity of the utility function actually amounts to risk aversion. The person rejects a fair game. Not playing the game gives us a higher expected utility than playing the game. Okay, that was the review of last time. Now let's go to the new concept of certainty equivalent. Now, a risk-averse person, a risk-averse agent, would pay a price to avoid a risky prospect or this risky game. I would be willing, to pay something. That's naturally what lies behind insurance. And here we have the definition of the certainty equivalent. It is a sure wealth that gives the same expected utility as the risky prospect. So we have here the expected utility of the game of the risky prospect, and then actually we ask, what is a sure wealth that gives the same expected utility as the risky prospect? Now I will illustrate this on the next slide with a graph, and then it will become more clear what we mean here. Anyway, mathematically, you can solve this for the certainty equivalent of this wealth that we're looking for. Just take the inverse function. So the -1 stands here for the inverse function. I'm using this notation for the inverse function. And this inverse utility function exists because the utility function is strictly increasing. Then you have an inverse. You see here we have the utility function, it's strictly increasing. And so the inverse must exist. So that's a topic naturally in mathematics. Okay, when does the inverse function exist? I try to draw you again here, even if it's not easy, a graph. Let's assume our utility function is different. It's again increasing, but then it actually starts to decrease after a certain, when Wells is very high. Now such a utility function would not have an inverse. You see the inverse would look somehow like that, but that's not the function. Because it's not unique. You see here actually we have one value, one function value, but then here we have another value. Now functions must be unique, else they are not functions. So the inverse only exists, okay, if you have strictly increases. The problem is here, okay, that actually it's declining here. That we have this declining portion here. So we assume a strictly increasing utility function, and so it will have an inverse. And because the inverse exists, we can quite easily solve equation 8. Now let's illustrate this equation 8 here again. So again, we have this fair game with 50% chance we win, with 50% chance we lose. The game is fair, so the expected value of the game is the initial wealth. So with 50% chance our utility will be high, and with 50% chance, okay, it will be low. And so the expected utility is just in the middle here. So that's represented by point B, we said. So that's the expected utility when we play the game. Now, if we don't take part in the game, our wealth is constant, and our utility is here, and that's also just equals expected utility, because as we said, okay, the expectation of a constant is a constant itself. So this person is risk averse in the sense that the person will reject the fair game. The expected utility of not playing is bigger than the expected utility of playing. Now the certainty equivalent, I have it here in red. The certainty equivalent is actually defined as a wealth which gives you the same expected utility as the game. That's here, this definition here. It's a sure wealth, WS, that gives you the same expected utility as the game. That's in equation 8. Now, let's now reduce here the wealth of the person. Let's take away from the wealth. So the expected utility of this certain wealth will start to decline from A to C. The question is, how much can we reduce the wealth? Okay, until we get the same expected utility as the game. So you see, as we reduce the wealth, this expected utility of the certain wealth will decline. And we can reduce it up to point C. At point C, the wealth is just, okay, such that actually the expected utility of this certain wealth is now equal to the expected utility of the game. So here, the expected utility of the game is equal to the expected utility of this certain wealth. That's the definition of the certainty equivalent. Now you can also go here in a stepwise fashion. Let's do this. So we have here point A, we don't place a game. Point B, we place a game. Okay, okay, we prefer point A. Now let's reduce wells a little bit. Now we still actually prefer this, not playing the game. If that's our reduced certain wells here, so now our expected utility of not playing the game will be here. That's still higher than playing the game, so we will not play the game. If we reduce the wells more, okay, then the expected utility of this certain wells here, we just take a bit money away from the person. So the expected utility of this reduced certain wells is still actually higher than the expected utility of the game. So we take away more and more wealth, and that's the maximum amount. This row here is the maximum amount of wealth that you can take away. If you take away more, okay, maybe you really reduce now wealth substantially, and that's your new certain wealth here. Then actually your expected utility after that certain wealth is now less, okay, than the expected utility of the game, and okay, you're actually worse off. Okay, so that's the definition of the certainty equivalent. It's actually sure wealth. It's a sure wealth. Sorry. It's a sure wealth. Okay, so that actually produces the same expected utility as a game. And we can solve it actually by inverting equation 8. Now at point C, we can say, okay, that the agent or person is indifferent between playing the game or between actually not playing. So at this point here, it does not matter. Now wealth is reduced so much, okay, so the expected utility is now just equal to the expected utility of the game. Okay, so it does not matter, because the agent will be indifferent between playing or not playing the game. Now this row here we call the risk premium. That's the maximum amount the agent is prepared to pay to avoid the game or the risky prospect. So this here is the maximum amount that the person is willing to pay to avoid the risky prospect. It's more expensive to avoid the risky prospect than actually the person will not pay. Okay, then actually certain wealth with such a big reduction in wealth, okay, to get rid of the risk. Okay, to pay for certainty, okay, would reduce and actually expect utility down here. And so it's actually better not to pay so much and to take the chances. Expected utility will be higher. Okay, so it's actually, so rho is W0 minus WS. So that's what you have here in equation 10. So a risk-averse agent would be willing to pay at most rho to avoid a fair game of coin flipping or just of a risky prospect, okay, of of winning or losing with 50% chance. Now this risk premium, the agent's risk premium, depends on the degree of risk aversion. That's a subjective component. It also depends actually on the probability distribution of the risky prospect. Okay, that's the objective component. This other one was a subjective component. It also depends, it may depend on initial wealth. This depends actually on the shape of the utility function. I illustrate the first 2 points on the next slide. More risk aversion means, okay, the utility function is more concave. We discussed that. You see, everybody will have a slightly different utility function. The utility functions just actually shows the tastes of people. Some people are more risk averse, other people are less risk averse, or maybe you even get more risk averse over your life. Okay, maybe when you are young, you're less risk averse, and when you're older, okay, you are more risk averse. So more risk averse means, okay, that you have a more strongly concave utility function. And you see here the rho will be bigger than here. So rho, this risk premium depends on the degree of risk averseness, how strongly risk averse the person is. That's a subjective component. So the utility curves are purely subjective. We assume that for most people they are upward sloping and they are concave. But remember, we could even have some risk seekers. We discussed that. I don't deal with a risk seeker. Well, a risk seeker may even have a convex utility function. The risk neutral one would have a straight utility function, a linear one. Okay, so how strongly risk averse is determines this risk premium here. It determines, okay, the maximum amount, okay, so it determines the maximum amount that the agent would be willing to pay, okay, to avoid the risk. Also, the probability distribution matters of the risky prospect. That's an objective component. That's what we have here in this second graph. You see here again have initial wealth, but now the H is bigger. So you either win, but a big amount, or you lose, also actually a big amount. So H is H plus or H minus. And again, you see here, okay, so rho will increase, so risk premium will increase. So more risk will increase the risk premium and the willingness to pay for insurance. And more risk aversion naturally also increases the risk premium or the willingness actually to pay for insurance. Paying for insurance reduces your wealth. Okay, you have to pay the insurance premium. Okay, that finishes this lecture of today. As I say, it's a bit more demanding here. Also, next lecture is a bit more demanding. So repeat this and last lecture, and then you will be well prepared for the next one. Thank you.